So, welcome all to the ninth week of the discussion session of the course Plates and Cells offered by NPTL. The course instructor of this course is Professor Sudeep Talukdar, and I am your teaching assistant. I am Asif Raza. I am a PhD scholar from IIC Bangalore, Department of Civil Engineering. So, without any further delay, let's start our discussion. So, we'll be discussing questions relevant to assignment 7. So the first question is the expression for the work done by the membrane shearing force on an element of plate of size dx by dy is. So as you have all studied in the module 7 lecture 1, work done by membrane force Nx in an element uh, dx by dy is given by the relation Nx by 2 del w by del x whole square dy. This is my work done. Similarly, work done by ny is given as ny by 2 del w by del y whole square dx dy, and work done by in plane shearing force nxy is given by nxy del w by del x del w by del y dx dy. So if we compare from all the options, the correct answer would be option A. Okay, so let's move on to the next question. A compression member of length A is compressed by the load P, which varies along the length of the column. If EI is uniform flexural rigidity of the column, then total load potential pi is given by the following equation. So here we need to notice is that P varies along the length of the column. So P is something a function of x. If I take x as my dimension varying along the length of the column, as you've all studied in the module 7 lecture 1, that the load potential pi due to bending and inclined forces are given by pi equal to d by 2 0 to a 0 to b del square del x square plus del square w plus 2 mu del square w del square plus 2 minus mu dx dy minus this will be 0 to a 0 to b due to the influence shear force is by 2 del w by del x square del 2 del w whole square plus nxy del w by del x del w by del y dx dy. So if we now reduce this to one dimension, our equation will come out as like reducing everything. To dimension x will get d will be like pi by 2. We take along x as 0 to a, so this will retain d square w by dx square whole square. Y will make it 0. Similarly this all terms, so this will be dx. Now minus nx will retain 0 to a. Nx would be is my px by 2 dw by dx whole square dx. So this would be my relation. So if we compare with all the options, so option A won't be there because p is my function of x. Option 2, let's see, yeah, first term matches. Second term also won't be there because p is my function of x. Option C, yeah, so option C is my correct answer. Option D won't be there because here the w would be my derivative. Yeah, that is dw by dx whole square. So option C is my correct answer. Now let's move on to the next question. The differential equation for a horizontal strut carrying axial load P can be written as this. In order to find out buckling load of the strut by finite difference method, the strut is discretized into 4 equal divisions of size L by 4, where L is the length of the strut. The node number at the center is 2, whereas the node at center is 2, whereas the node at the left and right of the center number 1 and 3 respectively. The deflection at nodes 1, 2, 3 are W1, 2 and W3 respectively. Application of finite difference equation at node 2 results in an equation A1W1 plus A2W2 plus A3W3. So we need to find the values of A1, A2 and A3. So okay, so first you need to know what is my element. So we have an horizontal strut element of length L, which is discretized into 4 equal divisions. So 1, 2, 3. So the center one has been named as W2, left one as 1 and 3. These are length L by 4, L by 4, L by 4, L by 4. Okay. So now this can be simplified as d square w by dx square plus p by ei w equal to 0. So for a second derivative we have like using finite difference method, we have L square w del x square at 0 is given as w minus 1 minus 2 w0 plus w1 upon h square. Okay, so in our context d square by w derivative will apply at the node center 2 plus p by e by w2 equal to 0. So this will give me w left one would be 1 minus 2 w2 plus w3 divided by the length of my element is L by 4 whole square plus p by ei, this would be w2 equal to 0. So Simplifying it, we'll get um, so we'll get W1 minus 2W2, so W1 plus, if I take this P by EI, this is for this 16, it will go down, so PL square by 16 EI minus 2 W2 plus W3 equal to 0. So this would be my expression, final expression. So if we compare it with this, A1 would be equal to 1, A2 is equal to PL square by 16I minus 2, and A3 is equal to 1. So correct option would be option 6, sorry, option C. So let's move on to the next question. Okay, so the number of half waves found in x and y direction for a square plate subjected to biaxial compression magnitude, and when the critical load for the buckling of the plate is reached are given by. This is simple, just the option be the first, m equal to 1 and equal to 1. Next question, the critical stress factor in buckling of simply supported rectangular plate subjected to uniaxial compression is always 4 for integral value of aspect ratio. So this is also true. You can see this in the last module. Determination of buckling loads of a plate is an eigenvalue problem. This is also true. You can see the equation just derived here, that is EI 2W dx square plus PW equal to 0, and of d2W dx square plus P upon EI W equal to 0. So if we see this is an operator kind of thing which is applying on LW plus kind of if you see, operator W is applying on here and is giving me a function something like this, lambda W. This is kind of, if you see in the matrix equation, Ax equal to lambda x. So this is an eigenvalue problem. So let's move on to the next question. Okay, so there is a square plate whose dimension is 600 mm. Thickness of the plate is 6 mm. Young's modulus is 2 into 10 power 5 Newton per mm square. Poisson's ratio is 0.3. The plate is simply supported along all edges, and the deflection of the plate is given by this expression. The plate is compressed only in one direction with uniform force P per unit width. Given load total potential by this expression, where W represents the work done by the compressive force according to Rayleigh-Ritz method, critical load P in Newton per mm for buckling of the plate rounded up to the nearest integer is. So first of all, we need to find this expression W, correct? So we are given with A equal to 600 mm, thickness of the plate is 6 mm, E is 2 into 10 power 5 Newton per mm square, Poisson's ratio is 0.3. Okay, now we are given with the expression W is equal to A sin by X by A sin by Y by A. And plate is simply supported along all edges. Now, uh, okay, so the load work done by the compressive force P would be given by it would be um, 0 to A, 0 to P by 2 del W by del X whole square dx dy, right? If you see, it is compressed only in one direction. So if we take nx is equal to p, ny is equal to 0, and xy is equal to 0. So work done by the compressive force P would be given by this relation. Now let's find del W by del X. So del W by del X is that would be equal to 5 by A, 5 by A cos 5x by A sin 5y by A. So this will give me the work done by the compressive load P as, okay, so this is A and D. 0 to A, 0 to A, P by 2 pi A upon A cos pi x by A sin pi y by A square dx dy. This expression is, let's write it again, 0 to A, 0 to A, P by 2 pi A cos x by A sin pi y by A square dx dy. So this P by P is constant. This P is constant per unit width, so I can take it out, and similarly this pi A upon A whole square also, so this would be equal to like pi A upon A whole square, finally 0 to A, 0 to A, this would be cos square pi x by A sin square pi y by A dx dy equals to P by T pi by A whole square times, so this can be integrated separately, 0 to A sin square pi y by A dy, and if we solve this, this will be value A by 2 and this will be also A by 2. So finally my work done by the compressive load P would be given by the expression P 2 to the 4 to the 8 P pi square A square upon this A square upon 8. No. So our load potential, total potential pi would then become as d pi for A square 2A square minus W, and W is equal to P pi square A square upon 8. So I need to find this load P using Rayleigh-Ritz method. Using Rayleigh rates method, I can take dou pi by dou A is equal to 0. So this will become 2 to cancel out. I can take 2A all over D by 4 upon 2A square minus 2P pi square A upon 8 equal to 0. That is, so this can be simplified. I can cancel A all throughout. This will give me, so I'll first write this again, 2 AD by 4 upon 2A square 2 AD by 4 upon 2A square minus 2P pi square A upon 8 equal to 0. This can be simplified as D by 4 upon 2A square is equal to P pi square upon 8. So this will give me P as 4 D pi square by A square. Now D is EHQ by 12, 1 minus mu square. E is 2 into 10 power 5. H is 6 mm. 12, 1 minus, this is 0.3, suppose here. So this would be equal to 3.9 into 10 to the power 6 Newton mm. Substitute this in this equation. 4 into 3.9 into 10 power 6 2 pi square by 600 whole square. This will give me, so let's check it. This is equal to 4 into 3.9 into, so this is equal to 433.33 into 10 to the power sorry, I'm not multiplied with pi. So 4 into 3.9 divided by 36. I have with me 10.2 into pi into pi. So this is equal to 427.68. 427.683 Newton per mm. Then so what I have to give is rounded up to the nearest integer. So if we round it off, this would be equal to 428 Newton per mm. So correct answer would be P is equal to 428 Newton per mm. Okay. Let me first check it once again to okay, so there is a mistake. Uh, yeah, that's what I was thinking. So correct value would be 433.83 Newton per mm, because this would be like 3.95 something. So if I round it off, it will be equal to 434 Newton per mm. Correct answer is 434 Newton per mm. I can just write 2 into 26 divided by 12 divided by 1 minus 0.3 into 0.3. I can write this as 3.95. Okay, next question. The critical stress for shear buckling in square plate of dimension equal to 800 mm is not to be exceeded 80 MPa. The material properties are Young's modulus is 2 into 10 power 5%, ratio is 0.3. Using Galeckian's approximate method for the buckling of the plate with the deflection as given below. The minimum thickness of the plate in is rounded off to the nearest integer. So, okay, so we are given that the displacement function as a1 sin pi x by a sin pi y by a and a2 sin 2 pi x by a sin 2 pi y by a. So we know, so we can write L of W as so we know okay. So plate equation is given by del to the power 4 W plus nx by d L square W del x square plus y by d del square W by dy square plus nxy 2nx by d del square W del x del y equal to 0. So in our case, we have only shear buckling. So nx is equal to 0 and y is equal to 0. Okay, so our plate equation reduces to del to the power 4 w del x4 plus 2 del to the power 4 del x square del y square plus del to the power 4 w del y 4 plus 2 nxy d del square w dx del y equal to 0. So I can write L del power 4 del x 4 plus 2 del power 4 del x square del y square plus del power 4 w del y 4 plus 2 nxy by t del square del x del y. Okay. So using Galerkin's method, we have 0 to a 0 to a L of w fn dx dy is equal to 0, which implies in our case two equations would be 0 to a L of w f1 would be a1 can just write sin pi x and pi y by a. So sin pi x by a sin pi y by a dx dy equal to 0. First equation. Second, 0 to a L w sin 2 pi x by a sin 2 pi y by a dx dy equal to 0. Second equation. So let's solve this one. Okay, so we need to find 1, 2, 3, 4, these 4 steps. So okay, so we are given that w is equal to a1 sin pi x by a sin pi y by a plus a2 sin 2 pi x by a sin 2 pi y by a, right? Okay, so first of all, the most simplified one would be this. Okay, let's solve it. Del w by del x is equal to, this would be equal to okay, so this would be equal to pi by a1 sin pi x cos pi x by a sin pi y by a plus 2 pi by a2 cos 2 pi x by a sin 2 pi y by a. Now del square w del x del y would then become okay, so this will be equal to pi by a whole square a1 cos pi x by a cos pi y by a plus this would be equal to 2 pi by a whole square a2 cos 2 pi x by a cos 2 pi y by a. Okay, so I have got one term. Now this, okay, so we need to find so we need to find this term. Okay, first we take this, so this would be equal to minus pi by a whole square a1 sin pi x by a sin pi y by a minus 2 pi by a whole square a2 sin 2 pi x by a sin 2 pi y by a. Okay, so now this I can take it as x to the power 4 is equal to, so similarly this, so this will be equal to pi by a to the power 4 a1 sin pi x by a sin pi y by a plus 2 pi by a to the power 4 a2 sin 2 pi x by a sin 2 pi y by a. Similarly, del to the power by 4 can be found as pi by 4 a1 sin pi x by a. You can just write it as equal to del to the power 4 w del by 4, and this one square del y square. This would also be equal to del power 4 w del x to the power 4. Okay, so now we have nxy as 80. Now substituting all these findings in equation 1 and 2. So from 1 we'll get just this one 0 to a and 0 to a, and the simplified thing like del power 4. So this is equal, this is equal, and this is equal. So this would be like 4 del x square so I have like L of w is equal to 4 del 4 w del x4 plus 2 to nxy by d del square del x del y. Correct. I can use this thing. Okay, so first do this thing. For pi by a for 1 sin pi x by a sin pi y by a plus 4 2 pi by a to the power 4 a2 sin 2 pi x by a sin 2 pi y by a multiplied with still plus 2 nxy by d del square w del x del y square del x del y. So this one. So this is equal to pi by a whole square a1 cos pi x by a and cos pi y by a. Similarly, plus 2 nx pi by d 2 pi by a whole square a2 cos 2 pi x by a cos 2 pi y by a multiplied with sin pi x by a sin pi y by a dx dy equal to 0. So if we solve this equation, it will reduce into pi by 4 a square a1 plus 32 and d nxy a2 equal to 0. Similarly, for equation 2, we'll get 32 nxy 9d a1 plus 16 pi 4 a square a2 equal to 0. So for non-trivial solution, pi by 4 a square 32 next by 90 32 90 16 by 4 square. This should be equal to 0. So this would imply that 16 by 2 to the power 8 a4 must be equal to 32 and xy 90 whole square implies that nxy must be equal to, so this would be like 4 by 4 a square 3 4 9 36 and so this would be okay, simply 4 by 4 a square, this is 9d by 32, so this would be equal to 3 the 9 3 4 the 2, so this is 32, so 4 8, so 9 by 4 d by 8 a square. So this is my nxy. Now, so I got my nxy as 9 by 4 d by 8 a square, and we have d as ehq by 12 1 minus mu square, and okay, let it come in here only, and nxy as sigma xy times h. So let's substitute. This is 2 into 10 to the power 5, 2 into 10 to the power 5 h cube 12 1 minus 0.3 square, and this is sigma xy is given as 80 times h, so 80h. Substitute all this in here, so we have 80h is equal to 9 by 4 8a is equal to 800 mm. 800 square d is 2 into 10 to the power 5. H cube upon 12 1 minus 0.3 square. So H cancel out. So H square would be equal to 80 800 square 12 1 minus 0.3 square divided by 954 2 into 10 power 5. Let's solve this thing. Get it over. Okay, so this is 80 times 8 into 800 square 12 into 1 minus 0.3 whole square divided by 9 into 5 to the power 4 into 2 divided by 5. So 20, this would be equal to 25.51 mm square. So H will come around okay, so this will be like 5.05 mm, but our minimum thickness should be greater than this value. So the minimum thickness H means should be equal to, and it should be an integer, right? So the correct answer would be 6 mm. So the correct answer is 6 mm. So this solves our last question for this session. That's all for today. If you guys have any doubts, please post it in the discussion forum. See you guys in the next week. Bye. Let's see once. Yeah, okay. That's all for today. Have a nice day. Bye.